Hello everyone, myself Pallavi Pujar. I am the chemical science expert of Rasayanika. So today I am going to discuss about the CSIR NET 2021 question paper. Okay, so before starting the question paper, let me ask you that how was your question, how you have done with the CSIR NET examination, and how did you feel about the exam, how it was like difficult or moderate or easy. Okay, so before starting the discussion, let me wait for 1 minute. The students are joining. So someone has joined. Mahesh Joshi. Okay. Good evening. And PJ Ahmad. Hello. Am I audible to you all? If I'm audible, please text in the comment box that I'm audible. Okay. So I can start with the conversation. Hello. Good evening. So, how did you feel about the question paper of CSIR NET 2021, which was being held in the Feb month? Okay, so we'll start the conversation with organic chemistry, means we start the paper discussion with organic chemistry part. Okay, so, okay, thank you. Okay, let me start the question paper then. Okay, hello, hello Rohini. So, easy section is C. Okay, so part B was moderate. Yeah, part B was moderate. Okay, let us start the question paper discussion. Okay. So I'm going to discuss about the organic chemistry questions. Okay. So in the first question what they have asked is the major product formed in the following reaction is. Okay. So they have given the reactant, that is 1,3-dichlorobenzene. Okay. So the 1,3-dichlorobenzene is treating with the concentrated HNO3 and concentrated H2SO4. Okay. So what they are doing, since from our PUC days, we are studying about the electrophilic aromatic substitution reaction. Right. So in electrophilic substitution reaction, what happens? The simple nitronium ion is generated where the nitrating mixture of concentrated HNO3 and concentrated H2SO4 both are reacting, where the HNO3 is protonated and the nitronium ion is generated and is attacking on the ortho or para position of the benzene. Okay, since they have given the 1,3-dichlorobenzene here, so we will get so many questions, right? So whether it will be para or ortho or meta. Okay, so here I can see that is 1 and 3. This is third position and this is first position. Okay, so in the given options, can you answer the question? Like there are 4 options are being given. One is at para position or ortho position, and B where the SO3H is attacked, and option C where the NO2 is at meta position, and option D where the SO3H is given. Okay, so just by simple this therapy, what we can say that the nitronium ion can generate, or the generated nitronium ion can attack at ortho or para position, right? So by looking at this example, we can understand that the option A is correct, right? So the option A is correct. So the option A where the nitronium ion is attacked at para position. Okay, if I consider this chlorine, so this is here 1, 2, 3, 4. Okay, so this is what the para position. So the nitronium ion is attacked at para position. Okay, next we'll move on to next question. Okay, so next question is the reaction that is expected to show a primary kinetic isotope effect for the indicated proton atom where the CH is mentioned. Okay, the in all the options whatever they have given, they have mentioned the CH bond. Okay, in option A also you can see, option B also you can see, option C also you can see, and even in the option D. Okay, so the CH they are talking with respect to the primary kinetic isotope effect. So if anyone knows the answer, can you give the answer in comment box? I guess no one is knowing the answer, or even though you are not knowing the answer, you are not answering. Okay, let me explain it in easy way. Okay, so first thing is we have to understand what is primary kinetic isotope effect. Okay, the primary kinetic isotope effect is what? Simple way we can say that in a chemical reaction, if we are carrying any chemical reaction, the change in the rate of the reaction can be seen when the change in the rate of the reaction can be seen when any one of the atom in a structure is replaced by its isotope. Okay, for example, here they have taken CH, right? CH is what? The hydrogen is replaced by its isotope. Its isotope is what? Deuterium. Okay, so in the first reaction you can see the benzene ring with CH is there, right? The benzene ring with CH, you can see here the CH they are talking with respect to. So the product what we have got, the bromobenzene we have got. So here they are talking about the bromination. Okay, the bromination of the reaction they are doing. So here this is also the electrophilic substitution reaction. As we know that the second step is rate determining step here. Okay, as the second step is rate determining step, the CH bond wherever we break or wherever we form, or it will not affect the rate of the reaction even though we change it by any one of the its isotope. Like if we change it by CD also, it will not show any effect. Okay, the rate of the reaction will be same only. So okay, next will be option B. So in option B, you can see that the benzene ring with OCH2, C double bond CH2 they have given, and adjacent CH bond they have shown. Okay, so here simple sigmatropic reaction is occurring. Okay, so here the sigmatropic reaction is occurring, and even it is not possible to show the primary kinetic isotope effect. And between option C and option D we have to answer. Okay, so let me go to option D. Okay, in option D what we have H2SO4. The H2SO4 protonates, and whether after protonation the H2O is kicked out from here, then the carbocation whatever is generated and it further protonated and it will be forming the alkene bond here. Okay, so even here it will not show the primary kinetic isotope effect. And next we'll go to the option C. Okay, so the option C is what? So answer is what? Option C. So option C is what? They have given acetone. Okay, so here they have shown the proton already, you can see that. So the proton already here we have 3. So any one of the proton I have to replace by deuterium. Okay, so what they have done, first we have to take the acidic media. If you are taking the acidic media, what I have to do? I have to do the protonate. What I have to protonate? I have to protonate the oxygen. So what I will do? I will protonate the oxygen. Okay, so I am protonating the oxygen, and the oxygen will be carrying the positive charge, and here it will be like what? Minus. Okay, so later what happens? In order to stabilize the oxygen valency, the electrons are moving here and the bond is shifted here. So what I can get? I can get COH, and this is double bond. Okay, what we have got? We have got enol. Okay, if we have got the enol, further what happens? The bromination, the Br2 they are adding. So here there is a Br2 where it is carrying partial positive charge, and further it is carrying partial negative charge. Okay, so the pi electron will be attacking on the bromine part which is carrying positive charge, then it will get OH, and here it will be Br, no? So later it goes out and I will be getting CO, CH2, Br. Okay, so here what they are telling with respect to the primary kinetic isotope effect is what? The CH bond, whatever here they have mentioned, the CH bond if I replace with CD, means this is CO and this is CH. Here I am replacing CD. Okay, the CH and CD, whatever if the hydrogen is replaced by the deuterium ion, there will be the change in the rate of the reaction. Okay, so according to the primary kinetic isotope effect, there will be a change in the rate of the reaction. So that is what is telling regarding the primary kinetic isotope effect. So according to that question, so the answer is what? Option C. Okay, so the answer is option C. Okay, if you have any doubts regarding this primary kinetic isotope effect, or any other questions, you can ask me. You can ping me in the comment box. Okay. So Satrupa is telling probably it is option B. Okay. Option B is not possible, as I have told. Here the simple sigmatropic reaction is occurring. So the primary kinetic isotope effect is not possible. And next we'll move to the question 3. Okay. So the question 3 is what? The major product formed in the following reaction is. Okay. So they have given one reaction. This reaction, we all are familiar with this. Okay. By looking at the reaction itself, we can say that it is one kind of condensation reaction. Okay. So the reactant, what they have given? Firstly, they have given the diethyl succinate. Okay. This is diethyl succinate. And they have given benzaldehyde. Okay, so the benzaldehyde and diethyl succinate are reacting in the presence of strong base, and the followed by the acid hydrolysis is occurring to get any one of the product. Okay, so the option 4s are given here: option A, option B, option C, option D, where some kind of the ester and carboxylic acid differences are made, right? So you can guess the answer easily if you know the Stobase condensation reaction. So this is one of the famous reaction that is called Stobase condensation reaction. Okay, so according to Stobase condensation reaction, if anyone knows about the condensation reaction of Stobase, you can give the answer in the comment box. If you know the Stobase condensation reaction, please ping the answer in the comment box. I guess you have studied most of the time in your master degree also, even during your MSc, BSc also. So I guess you know about the Stobase condensation reaction. If you don't know, I will explain. So if you don't know the Stobase condensation reaction, then let me explain about this question. Okay. So let us move to the explanation part. So what the reactant they have given? They have given diethyl succinate. So this is what the diethyl succinate they have given. Okay. So what they are doing? They are using base, that is TuBu. That is so this base, what it does? This base abstract proton, any one of the alpha proton, from this position also, from this position also. Okay, so any one of the proton is being abstracted. So from here I will abstract the proton. So if I abstract the proton from here, so the base will be abstracting the proton. So what I will get? So what I will get? The corresponding anion is generated. Okay, so here it will be like this. Okay, so further they have given benzaldehyde. So benzaldehyde, where it is having the carbonyl group, right? So the carbonyl center is what? The electrophilic, right? So what it does? The negative, the anion, it will attacking the carbonyl center. Okay, so once the carbonyl center is getting attacked by this, so what we'll get? We will get this structure. Okay, so here the pH is attacked and here oxygen. So one of the most important step in the Stobase condensation is what? There will be the formation of lactone. Okay, lactone is what? That is cyclic ketone. Okay, so I have to form the cyclic ketone here. So in order to form the cyclic ketone, what I will do? I will attack to the carbonyl group. Okay, if I attack on the carbonyl group, what I will get? I will get like this structure. So here it will be my pH. Simultaneously, if I am attacking on the carbonyl group, then the OET will be transferred out. So it is transferred out. Then how I will get? I will get my lactone ring here. Okay. So I am getting my lactone ring So you can see this is my lactone ring. Okay, so this lactone ring further opens. Okay, in order to open the ring, the proton from here, it will donate the electron here and it will be opening here, and what I will get my final structure as pH and CO2H and my corresponding ester. Okay, so here I will get my ester. Okay, so you can see the structure there. So there is the CO2 ET and double bond and COH. So Stobes condensation always yields the product, as it will be containing the alpha beta unsaturated carboxyl group and the ester also, that we call it as the half ester. Okay, so that is one of the famous condensation reaction of Stobes. Okay, if you have any doubt regarding the Stobes condensation reaction, if you want to explain this, if you want any explanation regarding this mechanism, you can ping me in the comment box. Okay, I hope you all understood. So we'll move to the next question. Okay, so next question is regarding the proton NMR. Okay, so easily they have given some proton NMR data. So what is the question? Which of the following compound has the proton NMR spectrum? That is, they have given 4 data. So according to this, the 2.4, 3.9, 7.25, 7.95. So, before understanding, doing the structure for proton NMR spectrum, let us see the options. Okay, the option A, option B, option C, and option D. Okay, so option A has ester group, and further at para position we have OMe, that is OCH3, and option B has the COCH3 group, and at para position we have the same OMe, and option C has at para position methyl group and the ester group, and the option D has COCH3 group and at para position methyl group. So before understanding the data for proton NMR, already we know that on benzene, without any substitution, the proton NMR of the benzene with the proton gives the chemical shift at 7.33 ppm, right? So it always gives at 7.33 ppm. So by understanding that, we can easily understand the answer. So in the structure A, if I look at the structure A, here there is a benzene, and here OMe, that is CH3, and here COOCH3. Okay, so as they have given the proton NMR values as 2.4 and 3.9, okay, that is for 3 protons they have given, that to one singlet. Okay, so there might be the possibility of these protons, these 3 protons will be giving one singlet, and these 3 protons will be giving one singlet. Okay, but here the environment changes, where this proton shift value, proton NMR shift, where the in chemical shift we can see it will give around 1.9 or something else, that ppm it will give. Okay, so as we know that, so option A is eliminated, we cannot give the answer as A. Next, option B, if I go to the option B, the same thing is there, but only the thing, the ester group is not there here. With instead of ester there is COCH3. Okay, even that is eliminated. In option C, option C, what we have the ester group and methyl group. Okay, so the ester group, whatever you can see above, it is like this. So this is COOCH3, right? At para position I have CH3. Okay, and option D, before explaining the C, let me explain about the option D also. Okay, so the same question, same in the option B, what we have seen at para position we were having OMe, but in the option D the methyl group is present. Okay, so even that is eliminated. Okay, so because that will not give the data value at 3.9. Next, when it is remaining, which option is remaining? The option C is remaining. Okay, so the option C here is what? The methyl group and COOCH3. So here I can have the protons also at this position, right? So there will be the presence of protons also, because they have given the 7.25 and 7.95 ppm value also for two protons, where they are giving doublet. Okay, so what they have given, the structure is like this: COOCH3, and here it is CH3. Okay, so this is proton, here one proton, and here one proton, here one proton. Okay, so COOCH3 is what? EWG. Okay, the ester group is electron withdrawing group, and here methyl is electron donating group. So the proton NMR value, whatever they have given, the 7.25 and 7.95, let me come to this first. Okay, the 7.95 for watt proton and 7.25 for watt proton. Okay, so the proton, whatever you can see, adjacent to the EDG group, they are present. Okay, so here these two protons, whatever I can see, they can give the proton NMR value at 7.25 ppm, because in chemical shift we know that the electron withdrawing group will be giving high range, whereas the electron donating groups will be giving decreasing range. Okay, in the beginning it like 1 2 3 like that. In electron withdrawing will be like 8 9 10 7 like that. Okay, so here the protons which are present around the electron donating group environment, so it can give the 7.25 ppm, and whereas the electron withdrawing group is present here, that is ester group, so these proton will be giving 7.95. Okay, further what is remaining, the 2.4 and 3.95 is remaining, right? The 3.95 already I have said that the electron withdrawing group will be giving high range, so definitely these three protons will be giving one singlet. So these proton will be giving one singlet at 3.95 ppm. Okay, and remaining these three protons will be giving one more singlet at 2.4 ppm. Okay, so this is what regarding the answer. So the option is C. Okay, so the given option C is correct, right? So if you have any question regarding proton NMR, you can ask. Okay. Okay, if you don't have any question, then I will move on to the fifth question. Okay, so the fifth question, whatever you can see here, is they are asking regarding the CO stretching frequency in IR region. Okay, so they have given the three structures. You can see there A, B, C, that is cyclic ketone they have given. Okay, so this can be explained easily. Here, whatever the structure A you can see, they have given without substitution, whereas option B, they have substituted the tertiary butyl group and the chlorine group, and here also they have substituted the same tertiary butyl group and the chlorine group, but the chlorine position in structure B and structure C is different. See, you can see here the chlorine is present in axial position, whereas the chlorine in third structure is present in equatorial position, right? So the structure which is present in axial and which is in equatorial position, based on that we can give the answer. Okay, if you know the answer of the CO stretching frequency in IR, you can give the answer in the comment box. So if you know the answer, please ping the answer in the comment box. Okay, so I guess let me explain this. First thing, the whatever the structure they have given, that is only cyclohexane they have given. Okay, the cyclohexanone, this is cyclic ketone. Okay, this cyclic ketone will be giving IR region at 1715. Okay, the stretching frequency can be seen, the band can be seen at 1715 per centimeter. Okay, and further what they have done, they have substituted with chlorine and tertiary butyl. As we know that the electron withdrawing group which is present on the cyclic ketone group, it will increase the wave number, that is the stretching frequency will be increased. So further, in order to explain the positions of the chlorine, so we have to explain this regarding its lone pair of electron. Okay, so in order to explain the lone pair of electron, here you can see the chlorine with whatever it is present here, it is in equatorial position, Okay, so the chlorine, whatever you can see here, it is present in equatorial position. So the equatorial chlorine, whatever you can see here, it will be having some lone pair of electron on it. There will be lone pair of electron like this. The oxygen will be having the lone pair of electron. So the lone pair of electron, whatever the oxygen and the chlorine are having, there will be some kind of repulsion between them. Okay, because of the lone pair repulsion between the chlorine and oxygen, the CO bond strength will be maximizing or minimizing. So there will be some kind of interaction between them. So because of that reason, there will be some change in their IR frequency range. Okay, so when I will come to axial position, the chlorine, whatever you can see in structure B, is far away from the carbonyl group. Okay, so there will be less effect of this lone pair of electron of the chlorine and the oxygen. Okay, so because of that reason, the structure C will be showing higher frequency range in IR spectrum compared to structure B. Okay, so anyhow, the structure A is kept at last only, because I have said already it will be showing its frequency range at 715 per centimeter. Okay, so the answer according to this is C, B and A. Okay, so the answer is C, B, A. So the option where you can see in the option C, you can see that, right? So the option C is correct. So the option C is correct. Okay, so let me explain, let me tell about our Rasayanika new batch. We are starting for the chemical coaching, that is chemical science coaching for the CSIR NET examination, with all hard copy study material we are giving, and there will be monthly practice exams. You can chat with us. We can clear your exams instantly. Your exam questions, and whatever the doubt you have, you can solve it immediately, and we will give the solution immediately. Okay, you can comment everything in Telegram app also, or else you can ping there. Okay, if you have interest, please ping in the comment box. That will give one link, that is Telegram link, so you can join the group there. Okay, so this is regarding our CSIR net coaching that we are starting tomorrow onwards only. So please do join the batch so you can crack the CSIR net. Okay, we will teach everything in better way and easy way. Okay. Okay, so we'll move to the next question. That is the sixth question. The major products A and B in the following reaction sequences are. So they have given the reactant here. So the reactant, whatever they have given here, with that they have given CF3CO twice O, and the PHH they are using, they are doing the reflux and will be getting structure A. And further the structure A they have taken and they are treating with the hydrazine, which is in acidic media. So they are doing the same reflux condition, and we are getting the product B. Okay, so the simultaneous options are given there: option A, option B, option C and option D. Okay, so if anyone knows the answer, you can answer in the comment box. So, okay, let us start the mechanism directly. So first reactant, what they have given DMAP. This is what DMAP they have given. Okay, and they have given CF3COO CF3. So CF3COO CF3, whatever they are using, what you can see here. So here they are doing simple acylation, right? The CF3 is broken down and it can be attacked at ortho position. So I am getting this ortho product. So this is my product. Nitrogen, here it will be as it is, and I will be getting COCF3. So according to this, the structure A is this. Okay, so let us move to the option. Wherever we have the acylated product, we can be done only at ortho position, right? So ortho position where we have, and in option A we have, and even in option B we have. What about the option C and option D? It is not possible. That is not possible. So option C and D is eliminated. Further, we are left with the option A and option B. That will be set. So like this, here whatever the option A I have, here the same structure will be taken and the COCF3 will be drawn here. So what they are doing, further they are treating with the hydrazine. Okay, so they are treating with hydrazine in acidic media. Okay, so what it does, it just removes water. Okay, so when it removes water, so I will be getting the structure as like this. Okay, so the structure will be CF3 will be as it is here, and the double bond in NH2. Okay, so the electrons are remaining on the nitrogen here. So further what happens, the lone pair of electron present over here, it will attack here. Okay, and it will be like this. The NCH3 will be here, and already the whatever I have shown the bond, it will not be there here, and here there will be nitrogen ring. Okay, so you can see, and the protons are there here, right? And the nitrogen will be carrying positive charge. Then what it does, in order to stabilize its valency, it will lose its proton. So the electron will be taking this proton, and further what I will get, so further I will get my end product as NNCF3. Okay, and the one proton is remaining as it is here, right? So this is my end product. So here you can see in the option B. Okay, so the option A is correct. Option B is not possible because they have done with respect to the para nitrogen, whatever you can see here, with respect to that they have done. Okay, so with respect to that they have done, so it is not possible. So the option A is correct. So let us move to the seventh question. Okay, so the seventh question, what you can see here, they have given the energy profile diagram. Okay, they have given one reaction where the two types of reaction are occurring, right? The diene is reacting and it is giving the bicyclic compound, whatever you can see, the Pa and Pb. Okay, so here we have to discuss with respect to their activation energy and with respect to their the product formation, means how much amount of energy they are means how much amount of energy is spending to form the product. Okay, so in order to explain that, first let us see the graphs whatever they have given with respect to their activation energy, the correlation they are giving with respect to their graphs. Okay, so in the option A, option B, and option C and option D, you can see the activation energy also, and the between the option or between the structure A and structure B and structure Pa and structure Pb, which is stable and which is having more energy, that is more matters here. Okay, so you can see here in the structure A and structure B. Okay, between structure A and structure B, which is possible, means you can see the structure A and structure B. Here it has 7-membered ring and here it has the 6-membered ring along with the cyclo-membered ring. Okay, that is 3-membered cyclopropane ring. So you can see here. So in the 7-membered ring and the cyclohexane, whatever you can see, the diene will be like this, right? So the diene will be like this, you can see here. So the diene is reacting with this and it is giving this structure, and the same this diene is reacting with this and it is reacting with, and it is giving me the product Pa. Okay, so here the product Pa and Pb and the structures A and B, means both are the reactants, different reactants which are having the high energy and high stable. We have to think about that now. Okay, between the structure A and structure B, structure A has more energy. Why? as already I have told that the 3-membered ring, whatever it is present, it is making it more, high energy. So because of its high energy, it is less stable. Whereas structure B is not having any such type of ring in its structure, right? Because there is no presence of such type of rings, it can be more stable. Okay, so what we have concluded? We have concluded that the B is more stable than A. Okay, so the B is further reacting with the this reactant and it is giving me this. Okay, and the same way the structure A is reacting and it is giving me this. Okay, so here also the same, on bridge head we can see the 3-membered ring. Okay, so as we can see the 3-membered ring on the bridge head, the same way the PB is more stable than PA. Okay, if it is more stable, in the sense what, the energy must be low, right? If it is having lesser energy, then it is more stable. So according to the graph, we have to check the options: option A, option B, and option C, and option D. Okay, so here in the option A they have shown the PA is below and PB is like this, and A to B, whatever the conversation they have given. So that is not possible. And in the structure, in the graph, whatever you can see here, the PA and the A is giving rise to PA and B is giving rise to PB. Even here, the B to PB, that is also not possible yet. And between C and D, whatever you can see here, the A is giving rise to the product PA and B is giving rise to the product PB. Okay, so here you can see that A to PA, whatever you can see, it can give the activation energy. So this is what I will call it as EA1, and this is what I call it as EA2. Okay, so the activation energy 1 and the activation energy 2, so both we can correlate. Okay, and the similarly in the option D also we can mark it. This is EA1 and this is EA2. Okay, so as I have said, the B is more stable than A and PB is more stable than PA. Okay, so the B to PB conversion and A to PA conversion, how much amount of energy is spending? Okay, activation energy, what, the minimum amount of energy is required to form the product. Okay, so in order to form the product, the minimum amount of energy must be spending. So according to option D, the activation energy, you can see there A to PA is more and B to PB is this much. So whatever they have mentioned, so that is not possible. And option C, whatever you can see, that is left and that is the correct answer. Okay, so that is what I have explained. Okay, so next let us move to the Newman projection question. Okay, this is one of the interesting question in CSIR NET, whatever they have asked. Okay, so let us solve this. So according to the Newman projection, whatever you can see there, so let me draw its chair form. Okay, so this is my chair form. Okay, so I guess you can see this, the cyclic rings. Okay, so here the CH2, whatever you can see here, right? So this CH2 is nothing but this CH2. Okay, so the CH2, whatever you can see, this is the bridge, whatever you can see, this is here. And further, let me mark the front carbon. So whatever you can see here, these are the front carbons. Okay, so these front carbons can be shown like this. Okay, so this is the front carbon, and further let me show the back carbon. So you can see in this given structure, given image, that the back carbon must be shown here. This is front carbon and definitely it will be the back, and this is front and definitely it will be the back carbon. Okay, so this is back, and this is front, and this is front carbon. Okay, so to this front carbon, one more CH2 is there and it is attacking here. Okay, so to this here, whatever I have marked here, so that can be shown here. So that is nothing but this CH2. Okay, so you can see with yellow color I have shown that this CH2. Okay, so this CH2 is nothing but this. Okay, so further what they have done, this is, so if I am showing this, then definitely it will be my front carbon. Okay, then it is my front carbon, and to this the back carbon will be shown like this. So this back, whatever you can see, this is back to this carbon. Okay, so now I can understand by looking at the image that the front and back carbons, which and all I understood. Now I have to check the methyl group where it is present. Okay, so in order to mark the methyl group, let me mark. Okay, so let us mark the methyl group. So here on the front carbon, as I have said, this is the methyl, that is CH2 bridge, whatever I can see. To this there is one CH3 which is in equatorial position, and there is one more hydrogen in axial position that you can see there. Okay, so here it is in equatorial position, and the one hydrogen is in axial position. Okay, to this next what we have further, to this front carbon we have hydrogen. Okay, again the same bridge, whatever you can see here. So this, to this carbon, again we have only two protons, right? So we have only two protons. Okay, further the CS3, whatever you can see, the CS3 whatever you can see here, it is on back carbon. Okay, so the CS3 whatever you can see, it is on back carbon, so that can be shown like this. And at axial position one hydrogen. Okay, so the CH3 whatever is present here in equatorial position, and here is also equatorial position, so that is nothing but both the methyl groups are in below the plane. Okay, so if both the methyl groups are in below the plane, how exactly the structure looks like? Okay, so how exactly it looks like? So as I have said, so let me mark the bridge so you can understand. So this is nothing but my this in structure, whatever I have shown with black color, you can see this is my bridge, so which is connecting two rings. Okay, so this is connecting two rings to this 1 2 3 4. Okay, if I count from here 1 2 3 4. Okay, so let me go with the white pen. Okay, so with respect to this, I can see at fourth position I have methyl group. Okay, so with respect to this, if I have the fourth group, so here it will be like this, and here like this, and further the hydrogen is remaining like this. Okay, so if the hydrogen is remaining like this, then we can see both are in below the plane. Both the methyl groups are in equatorial position, in the sense they are present in the below the plane. Okay, so that I have shown. So according to this, the answer is option A. Okay, so just by looking at the methyl group itself, we can understand. Okay, in order to understand the structures, always we have to draw in chair form. Okay, so as I have shown the CH2, and here also one CH2, that one CH2 and one more CH2, this CH2 and this CH2, as already I have shown in the structure. So the methyl groups and methyl groups, so whatever I can see here, here is, there is one methyl group and one methyl group which are in below the plane. Okay, so that is what the answer is, option A. Okay, if you have any question regarding the Newman projection, you can ask me. Okay, if you have any question, you can ask me. Okay, so let us move to the next question, that is the correct sequence of reagents that will lead to the formation of the given product in the following reaction is. So they, here they have given the reaction and it is giving one product. Okay, so how exactly it is forming the product? So just by looking here, what we can see, So just by looking here, what we can see, the ring whatever they have given here, this is OH and here OH. Okay, so if I choose option A, then they have given the active MnO2 and methyl iodide NaH, and thirdly they have given the sulfur ylide, and fourthly they have given the Wittig's reagent. Okay, in the presence of base they have given, and option B is having the same methyl iodide, sodium hydroxide, and active MnO2 and all they have given. But if we do not oxidize this, how further the reaction will be occurring? So it will be not possible. It's right. So according to that, in order to oxidize the reaction, first we'll choose the option A as the correct answer, because they have given the active MnO2. As we all know that the active MnO2 always oxidizes the allylic alcohol. Okay, so there will be the MnO2 and it will oxidize this alcohol. Okay, so it will oxidizes to CO group. Okay, so once it oxidizes, further what they have given, they have given methyl iodide in the presence of NaH, that is base. Okay, so they are using NaH, that is a base, and methyl iodide. Okay, methyl iodide, for what purpose we do use? We do use it for the alkylation. Okay, for alkylation, whatever the methyl will be attacking. Okay, so in the presence of base, the proton will be eliminated and we'll be getting OMe, because here once the NaH removes the proton, the methyl will be acting and it will be attacking on the oxygen. Okay, so I will be getting this structure. And further what they have given, so this is 1 and this is 2, and third reagent what they have given, as I have said, it is sulfur ylide. Okay, so they have given the sulfur ylide, that is Me thrice SOI. Okay, in the presence of base. So in the presence of base, what it does, it will directly form the cyclopropane ring here. Okay, so it will form this type of ring. Okay, and further what they have given, they have given the MEPPH thrice BrNaH. Okay, in the presence of base they have given, that is Wittig's reagent. Wittig's reagent, as we all know that it will convert the aldehyde or ketone into alkene, right? So the product will be OCH3. Right, so this is what the correct reagents they are using in order to convert this product. Okay, so what they have done, in the beginning they have taken the MnO2, that is manganese oxide, which is used for the oxidation, which selectively oxidizes only the allylic alcohol or benzylic alcohol. Okay, so it is oxidizing to give the ketonic group. Okay, so it will oxidizes and it gives the ketonyl group here. So you can see, and further they are treating with the methyl iodide in the presence of strong base. Okay, so they are using the strong base, and the methyl iodide is used where the proton is abstracted from the oxygen, and further the methyl iodide where the methyl group will be attacking on the oxygen. Okay, so the methyl group, as I have shown, it will be attacking here, and further they have used the sulfur ylide. Okay, the sulfur ylide will be forming the three-membered ring where the alkene is present here. So the sulfur ylide will be forming the three-membered ring, and further it will give rise to product that double bonded carbon where they have used the Wittig's reagent. Okay, so in the presence of Wittig reagent, we are getting this as the final product. Okay, so the option A is correct. Okay, so if you have any questions regarding this mechanism, you can ask me. I guess you don't have any doubt because I'm clarifying everything correctly. So organic chemistry is not much difficult. It is very easy as we play the games. But only the thing we have to understand where to break the bond and where to form the bond. Okay. So the mechanism, whatever I can show here now, it will be very simple and you will be understanding it in easiest way. Okay. So the last question, whatever I can say here, it is the major product formed in the following reaction is. So they have given the reaction here in the presence of MENH2, that is the methyl amine, where this is one of the interesting reaction. Okay, so here it is acting as both base also and nucleophile also. Okay, so how exactly it will be acting as a base and nucleophile, we'll understand it by using its mechanism. Okay, so the first structure they have given here is this. Okay, the NH they have given, and there is one double bond and CO, and here Br is there. So here what happens in the presence of base, that is MENH2, what it does, first it will abstract a proton. So what it is acting as, so it is acting as a base right now. So what it does, it will abstract this proton. So once it abstract the proton, so I will be getting like this. Okay, so further what it does, further there is one pi bond. When it donates it electrons here, it will to here. Okay, so it will be like and this is Br. Okay, so there will be negative charge. Once the Br goes out, it will go here. So what it can form, it can form the benzene ring with nitrogen here. Okay, so the nitrogen here, so the nitrogen here, and it will be forming 3-member ring. Okay, so this is what I have got now. So now what is happening, till now the MaNH2, that is methyl amine, is acting as a base, and now it has to attack as a nucleophile. Okay, so in order to attack as a nucleophile, the MaNH2, where electrons present over nitrogen, will be attacking on the carbonyl carbon. Okay, so once the MaNH2 attacks on the carbonyl carbon, so I will be getting structure as this O minus. So let me show here. So whatever I have got till now is like nitrogen, and there is CO minus and NH, Me, and there are 2 methyl groups. Okay, so here double bond is there. So I have to break the 3-member ring now. So this 3-member ring, in order to break that, I have to donate back these electrons to oxygen. So then automatically the bond will be broken here. Okay, so what I will get is CH3 CO NH Me. Okay, so this is what my final product. So as you can see here. So as you can see, the final product between A, B, C option and D, where you can see this, you can see in the option C. Okay, so in option A, what they have done it different way, where they have formed it different way. Okay, where the NHMe is there, And here between the option C and option A, what you can see here, that is the two methyl groups are gone out here and the CO is somewhere else, like that. So this is not possible and the option C is possible. Okay, so nothing they have done, so just they have taken the reactant where they are treating with the methylamine base, where it is abstracting the proton from the nitrogen. So once it abstract the proton from the nitrogen, so then what happens further, the electron will be shifting in order to form the three-membered ring. Okay, so it is forming three-membered ring, and after three-membered ring formation, the methylamine is acting as a nucleophile. Okay, so as I have explained, it is acting as a nucleophile here, and it is attacking on the carbonyl carbon, and further it will be giving, in order to the cycle will be opened, and it is giving me a product as C6H5, the 5-membered ring, CS3 twice, and CONHMe. Okay, so this is what the option C is correct here. So today I have solved about 10 questions of organic chemistry, and further I will be coming with the next session of the remaining organic chemistry questions. So where I will be solving about the Proton NMR problems and regarding some other stereoisomers also. So the CSIR NET question paper, whatever they have asked regarding organic chemistry, somewhat like it was moderate. Not all questions were direct. Even though paper was easy, it was quite difficult to think in the beginning, but it was very easy to understand. Means only the simple basic questions they had asked us, right? So the only the simple basics, if we can understand, we can crack the exam easily. Okay, in order to crack the exam, always we have to start with the basics. Okay, if we don't know the basics, so better improve your basics, then you can go ahead with the solving with the questions or the question papers or the mock test also you can do. Okay, so I will be coming with the next live session on organic chemistry part 2, where I will solve some more questions of CSIR NET 2021 questions. Okay, so as I have said, our Rasayanika batch, we are starting from tomorrow. Okay, if you want to join Rasayanika and if you want to crack the CSIR NET exam with easiest way, so you can join our batch. Okay, so we will solve all type of questions, and even we will moderate and we will simplify our teaching method also, so you can understand once how the cracking exam is easy by joining Rasayanika batch. Okay, so already I will the Telegram link is being pinged in the comment box, so you can join. Okay, so once you join, you can understand easily, and we can cover all the syllabus of CSIR NET chemical science, whatever the syllabus you can see. In the beginning it will be difficult for you, but we will make it simplest way. Okay, so let us crack the CSIR NET exam without making it difficult. Okay, so just think in the basics way, crack the exam and achieve your goal. Okay, I will be coming in the next live session. Okay, thank you.